Let us study magnetic effect of electric current. With the help of a diagram, we will study what is magnetic effect of electric current. Now this magnetic effect of electric current proved by or shown to us by a scientist. His name is Hans Christian Ørsted. Hans Christian Ørsted. Now we will study the experiment which he had done in his time. In his experiment, he proved that electric current as well as magnetism are related. Electric current we can call it as even electricity. So the experiment which he had done, in that he proved that two things are related. They are electricity and magnetism. Both of them are related. Now here we kept one circuit. Now this is the cell. Here we can call it as battery. Two cells are connected. So I written here battery. Now current flow is taking place from positive terminal to the negative terminal. Now here we can find that when current flow is taking place from positive to negative terminal, that particular time towards where the current flow is taking place, towards which direction current flow is taking place, towards that direction you can find that this, here I am keeping north pole of the magnetic needle, here I am keeping south pole of the magnetic needle. So here you can find that as and when current flow from positive terminal to the negative terminal, you can find that the magnetic needle shows deflection towards the direction where current flow is taking place. So here deflection is showing by north pole of this magnetic needle. As a result of it, you can find that here now this magnetic needle is deflecting towards the direction of the current. Now if we are changing the terminals, that means now here positive terminal, here negative terminal is there. Now instead of that, if I am keeping this terminal here, so again I am showing with the help of other diagram. Here now positive terminal I am keeping here, negative terminal I am keeping here, just reversing the terminals of the battery. Here I am keeping the key. Now current flow will be from here towards there, you can see. So the poles, here again I am keeping, this is the north pole, this is the south pole of the magnetic needle. This is known as magnetic needle. Now here you can see that current flow. Now what is happening to this magnetic needle that we are seeing? So here now this place you see that as and when current flow taking place from positive terminal to the negative terminal towards where current is flowing towards there, this north pole of the magnetic needle deflected. Now here magnetic needle be fixed and kept. So you can find that current flow is taking place from positive terminal to the negative terminal. So that particular time you can find that this north pole moving downward direction. So we can say that now at present the current flow is taking place from positive terminal to the negative terminal. At the same time here direction towards this side. So you can find that north pole of the magnet moves downward direction. So from this we can say that as and when current flow is taking place through the circuit, the deflection occurs in the magnetic needle. In other way, if we are explaining, as and when current flow is taking place from positive terminal to the negative terminal, the pole, here you can see that towards which direction it is flowing, towards that direction magnetic needle deflects. So here north pole is there, so north pole deflects towards the direction of the current. In this case, the current flows from positive terminal to the negative terminal. So you can see that here the direction of the flow is towards this direction. So you can find that at the same time this south pole deflects. So towards which direction current flows? Any one pole of the magnet deflects towards there. Here towards this direction north pole deflected, as north pole is kept here. Now here towards here south pole deflected, as we kept the south pole of the magnet in this direction. So towards which direction current flows, towards that direction you can find that the magnetic needle deflects. So two ways of deflection we studied here. One thing, north pole deflected here as and when current flow towards there. But once the flow of current in opposite direction became, that time you seen that north pole deflected downward direction. That is one experiment. Second thing we can say that as and when current flow towards which direction, there which pole is there, that pole is pointing towards there. Here north pole is there, towards the direction of the current, this north pole deflected. Here now flow of current from this direction towards here, this way its flow is there. So here you can find that south pole is deflecting. So from this experiment we can learn that magnetism as well as electric current or electricity are related to each other. Now we will study magnetic field produced around the conductor. So for doing that, one experiment I am showing you. Here, for studying magnetic field produced around a conductor, first I am taking one thick copper wire. Then that thick wire I passed through a cardboard. After that we have to make the circuit with the battery, rheostat as well as key. Now what is the use of rheostat? Rheostat helps to change the resistance of the conductor. So resistance already you people studied. Resistance is a coil of wire. Now its resistance, that means the resistance normally remains constant. So for changing the resistance of the resistor, we have to use a rheostat. Now that diagram also I will draw and show you. So here now this is the thick copper wire that I passed through the cardboard. Now remaining experiment with the help of the diagram I will explain. So here we are studying now magnetic field produced around a conductor. For that, I am taking a cardboard piece. Through that, I am passing one thick copper wire. Thick copper wire. This copper wire I am connecting with the circuit. Here I am making the rheostat. Rheostat will be there, same as resistance, there will be one arrow mark on it. After that, I am connecting here one ammeter. A means here an ammeter I am connecting. Ammeter. Then afterwards a cell connection I am doing. Two cells I am connecting. This is positive terminal, this is the negative terminal. Afterwards I am connecting with the key. Now, so here in this circuit, here this copper wire I taken, that is connected with the other copper wire. Then here cell, key, one ammeter. Ammeter's function to find the current, how much is passing through this circuit. So for that ammeter we are using. Here then one rheostat is connected that has the capacity to change the resistance of the conductor. Now here current is passing through this wire. So at first I am connecting and keeping one magnetic needle. One magnetic needle I am keeping here. So we can, when we keep a magnetic needle, as and when current flow through this circuit, if we are keeping this magnetic needle near the current flowing conductor, you can find that more deflection is occurring to the magnetic needle. If we are keeping this magnetic needle far from it, so you can find that there will be less deflection. So if we are keeping magnetic needle here, now current flow fixed condition I am keeping. That means here two cells connected, current flow now fixed condition. At the same time, when we are keeping magnetic needle near to the conductor, you can find that there will be more deflection on magnetic needle. Here current constant we are keeping. Current flow constant. Current flow constant means the number of cell we are keeping constant. Cell number constant I am writing. So there will be the number of cells constant, as a result of it current flow constant. Now only we are doing one work, moving of magnetic needle. If we are keeping magnetic needle near to the current flowing conductor, you can find that this magnetic needle shows more deflection. If we are keeping magnetic needle far, you can find that there will be less deflection on magnetic needle. If you are keeping magnetic needle near to the conductor, you can find that it deflects more. At the same time, if you are keeping the magnetic needle far from it, you can find that the magnetic needle shows less deflection. Now one more way we can explain. Now magnetic needle we are keeping in one fixed place. Magnetic needle we are keeping in one fixed place. But at the same time, we are now at first I am keeping only one cell. That means the current flow less I made. Here now only one cell I kept, magnetic needle I kept fixed, but current flow changes. So here we can say that we are doing the change in current. That means current flow, in that we are doing some changes. So here we can say that here we are using only one cell now. That means current flow less we made. At the same time, this magnetic needle we are keeping in the fixed position. Magnetic needle we are not changing. Magnetic needle we are keeping in the fixed position. At the same time, number of cells keep on changing. So at first we are keeping now one cell. So you can find that here deflection less. Less deflection in the magnetic needle you can see. After that, we are increasing the number of one more cell. Now current flow, one more cell I put it here. So as a result of it, current flow increased. When current flow increases, you can find that deflection shown by the magnetic needle more. If you are keeping current, here first I kept a one cell, second time I am keeping two cells. So we can find that deflection shown by the magnet more. Magnetic needle we are not changing here and there, we are keeping in fixed condition, but we are changing the current flow. So we can find that if we are, or when we are changing the flow of current, or when we increases the flow of current, we can find that the deflection shown by the magnetic needle is more. Now, so from this experiment we can study two important things. One thing, if you are keeping the current constant, that particular time we have to move the magnetic needle either close to the current flowing conductor or far from it. If you are keeping the magnetic needle close to the current flowing conductor, you can find that magnetic needle shows more deflection. But when we are keeping far from it, you can find that magnetic needle is showing less deflection. So in this case, if you are keeping this constant, then magnetic needle we have to move here and there. If you are keeping the position of the magnetic needle in constant condition, then we have to change the amount of current flow. If we are increasing the current flow, here deflection shown by the magnetic needle will be more. If we are reducing the current flow, the deflection shown by the magnetic needle will be less. Now, with the help of iron fillings, again we will study the same experiment. So magnetic needle I am removing now, but instead of magnetic needle, I am spreading and keeping iron fillings. Iron fillings means iron particles. Iron particles means small pieces of iron. Now again I will show here. Same experiment. Here such a condition, we people are passing the copper wire through the center of this cardboard piece. Now on that we people are sprinkling and putting iron fillings. Iron fillings means iron pieces. Very tiny pieces of iron. After that we have to complete the circuit as shown here. Then we have to give a little tap like that. Slowly we have to tap this cardboard. So you can find that iron fillings forms concentric circles around this current flowing conductor. concentric circle means one center will be there, around that many circles are forming. So we can say that all the circles will have one center or same center will be there. Now with the help of the diagram we will study that. Here just I sprinkled it, then as and when current flow starts, we can find that these iron fillings forms concentric circles. On its own they will form. Just we sprinkled, then we just tapped. Tapped means just we hit it slowly. So you can find that iron fillings forms concentric circles around this current flowing conductor. Now from this we can learn that the fillings or iron fillings which are near to the conductor, they are coming very close to the conductor. At the same time, again we can see that nearby area, how much concentric circles are there. They are present in the crowded condition. These all iron fillings formed concentric circles, but you can find that they are very close by circles. But at the same time, the iron fillings which are far from it, you can find that they are forming big circles. Like that. So that means the gap between them is very far. But at the same time, the iron fillings which are near to the conductor, they form very close by concentric circles. So from this we can find that here means which all particles are near to this rod, or we can say that this wire, copper wire. So their magnetic field formation is more. So here we can say that magnetic field formation near this conductor is more, far from it is less. So we can say that magnetic field formation, or we can say the pull, the attractive force between this copper wire as well as iron fillings more, if it is nearby. Now far away iron fillings, with them the magnetic field formation is less, or the attractive force is less. Because of that we are finding that here means far iron fillings are forming. Then later means no concentric circles formation also will be taking place. You can find that here and there iron fillings are lying, they are unable to form the concentric circles. So from this experiment we can understand that when current flows through this conductor, near this conductor how much iron fillings are there, they form concentric circles very close by. We can say that concentric circles, you can see that very much crowded condition. So from this experiment we can learn that the magnetic field produced by this copper wire, that is more around it. That also we can say that very close by area. So this close to this copper wire, more and more attractive force will be, or more and more magnetic field formation will be there. Far from it, then pull will be, or attractive force or magnetic field produced by the copper wire will be less. Now one more thing I am saying you. Now this copper wire, this cardboard I fixed here, iron fillings I am keeping here. Now if I am keeping far, then also same process will take place. If I am keeping far again, that means any part around this copper wire, if you are keeping this cardboard as well as iron fillings, same process will happen. So we can say that concentric circle around this conductor will take place any point on this wire. Anywhere we can keep, same process will take place. So we can say that anywhere around this conductor, everywhere magnetic field formation is taking place. Because of that, it can be able to attract the ion fillings towards it. As a result of it, concentric circles are producing by the ion fillings. Now we will study what is right hand rule. So first, with the help of an experiment, I will show you what is right hand rule. What is right hand rule? With the help of experiment I am showing now. You have to just imagine. You are holding, just imagine this is a current carrying conductor. That means the full circuit is completed, current is flowing. That copper wire we are holding with our right hand. Like that. So imagine that. That means current carrying wire you should not touch. So just imagine you are holding. This is a copper wire. That is a real thing. But it is not connected with the circuit. But you have to imagine that this copper wire already connected with the circuit. Now current flowing through it. Then such a copper wire you are holding with your right hand. Like that. Then what is saying? Imagine that you are holding a current carrying conductor with your right hand. Then the thumb shows the direction of the current and the fingers which turned. It shows, that means towards which direction it is turned. That is showing the direction of the magnetic lines of force. So we can say that curled fingers. These are the curled fingers. Their direction towards where? Towards here. So we can say that curled fingers shows the direction of the magnetic lines of force. Thumb shows the direction of the current. Curled fingers shows the direction of the magnetic lines of force. Then direction of the magnetic lines of force will be towards where we are folding it or turning it. Towards that direction, the direction of the magnetic lines of force will be there. Now we will study another topic, that is a magnetic needle produced by current through a circular loop of a conducting wire. Now with the help of a diagram we will study that. For studying that, we have to take one cardboard piece. Here I taken such a cardboard piece which is having two holes. Same way here I am making two holes to this cardboard. So just imagine such a cardboard, on it two holes we have to make it. Through that we have to pass one loop of the wire. It can be many loop. Loop means a circular wire, I can say. Such a way, one loop, two loop, three loop. Like that way number of loop we can be able to make it. After that we can connect it to the circuit. If more loop will be there, more number of coils will be there, we can say that magnetic field production will be more. Magnetic field more will be there. If only one coil is there, one loop is there, loop means a circular form. If we are turning a such a way, if we are making such a round form, that means now it is a straight one, very strong one is there. If we are making its like that way round shape, then we are saying it as loop. So here only one loop is there, that one we are connecting to the circuit. So we can say that here magnetic field production will be less. Here number of coils, more and more coil if you are using, like that way loop more and more if you are making. So we can say that more and more magnetic field formation will be there. Now here how it is taking place, we'll see. Now through here, two holes are there. Through here I am passing a coil of the wire. Like that way, a round shaped coil of the wire I am passing through this. After that I am connecting this with the circuit. In this circuit we can keep the cell. After that we can keep one ammeter. Then we can connect one key also. Now we can find that here current flow will be from positive terminal to the negative terminal. So such a way current flow will take place. Then it will pass through this. Here this way it will flow. This way, then this way it will pass. Then again it will come. We can say that here now when we are passing the coil through here, such a way will be there. This end will pass through the other hole. That is only I shown here. Then its end region here reached, then that thing I connected with the circuit. Now you can find that as and when current flow through this circuit, even we have to sprinkle iron fillings here. So you can find that near this loop, you can find that concentric circles will be crowded. Same way, two places you can find the concentric circles. Near both the loop you can find that concentric circles. After that, far from this loop, which all concentric circles are forming. Like that way again you can see the concentric circles. At last you can see that when it is coming at the middle part, there you can find that the arc formation will be a straight line. Like that way straight line like a formation will be there. Now here again the connection, we can say that here north as well as south direction connection is shown here. So you can see that here the central region, once it is reaching these concentric circles, you can find that they are forming in which condition? Straight line condition. Middle or nearby, near to this loop, you can find that the intensity of these concentric circles will be very much crowded. Now one more thing is there, as I shown you before, here means any part, if you are keeping, the attractive force will be there, as I told you before, through this conductor. Current flow is taking place. So it's any part, magnetic field formation will be there. Same way with it, if you are making such a loop, you can find that everywhere, say with the same intensity, we can say magnetic line formation will take place or magnetic field formation will take place. So each and every part on this copper wire, or we can say the conductor, magnetic field formation will be taking place in the same way. This is now a straight copper wire. If you are making its circular form, we can say that it's a loop form. Then also its magnetic field formation will be each and every part, we can say, not here alone. If you are keeping here, here also it will be there. Here also same, here also same. So it's each and every part will have the same magnetic lines of force formation or magnetic field formation will be there. If a single loop if you are keeping, single coil if you are keeping, so we can say that magnetic lines of force or magnetic field formation will be less. At the same time, number of coils, number of loop if you are connecting and keeping together, so we can say that magnetic field formation or magnetic lines formation will be more. Now we will study magnetic field due to current in a solenoid. Now what is solenoid? Solenoid means, just imagine a large spring. Now let us see or let us study with the help of the diagram. Here I am drawing first the diagram of a solenoid. Solenoid spelling SOLENOID. Now solenoid as well as a bar magnet, both of them are related. How bar magnet is acting, same kind of action even solenoid can do. But bar magnet is a hard substance, thick substance. But a solenoid is like a spring. First I am drawing one bar magnet. Its action first I will explain. This is the north pole, this is the south pole of the magnet. We can say that the magnetic lines of force producing from north pole to the south pole of the magnet. You people already studied in the previous class. So magnetic field formation or magnetic lines formation is taking place from north pole to the south pole. Then again you people studied that near the surface of the magnet, maximum magnetic lines formation will be there. Far from it, magnetic lines of force will be very less. Then you can find that even they are unable to form the magnetic lines. So similarly here also, north pole to the south pole, magnetic lines formation is taking place in the bar magnet. Where far away area is there, their magnetic lines formation is not happening. So here it is starting, magnetic lines of force is starting from north pole and ending at the south pole. So here we can say that magnetic lines of force produced by this is the bar magnet. Bar magnet, it is produced magnetic lines of force. Or we can say magnetic field formation. So in this figure we shown that this is a bar magnet that is produced magnetic field lines or magnetic lines of force. Now magnetic lines of force starting from north pole and ending at the south pole. Similarly here also starting from north pole and ending at the south pole. Now inside this bar magnet, magnetic lines are moving through or moving from, we can say, south pole to the north pole. You see here it is coming and joining here, again it is passing through. So we can say that inside the magnet, magnetic lines of force or magnetic field lines moving from south to north. Inside this magnet, magnetic lines moving from south to north. But outside the magnet, magnetic lines or magnetic field lines moving from north to south. Now similarly, I am drawing and showing you solenoid action, works, magnetic field formation, everything same as bar magnet, but how it looks, that I am showing. Here I drawn bar magnet and its magnetic field lines. Now I am showing you what is solenoid. Solenoid, as I told you, it is a big spring-like, but it is made with the help of copper wire. Then its circuit formation all very simple. Now two ends will be there that we have to connect to the cell as well as key. This is the solenoid. Solenoid's inside part is not having anything. It is empty. Spring, how it is there, inside will be hollow. So I can say that inside part of solenoid. Here I am writing now what is solenoid. Solenoid is acting like a bar magnet. Now this heading I am removing from here and I am putting here because this is the bar magnet. Now this solenoid, it is like a spring, but it is not made with iron, it is made with the help of copper wire and its inside is hollow. Nothing is there. It is acting like a magnet as and when we pass current through here. This is positive terminal, negative terminal. Now we are passing current through here. As a result of it, the current flow through this coil. Afterwards again it is reaching to here. Now as a result of it, it is acting like a magnet. Now we can find that here from this one side I am putting, this is the north pole and this is the south pole of this solenoid. Now we can say that here the formation of the magnetic field lines. So here this I am writing outside. Now again through here. Everything is happening as bar magnet. Magnetic field line from north pole to the south pole. Similarly here also I am making it. Or I am making its size smaller because the magnetic field lines won't be such a large. Here I am making it small condition. Here the cells connection I am showing. This is the positive terminal, this is the negative terminal, here the key connection. Now you can see that magnetic field lines from north to south. North to south its formation will be there. As you studied now, the magnetic field lines in case of bar magnet, same to same formation is taking place from north pole to the south pole. Again we can say that from here you can find that this is a hollow part I am rubbing now. Now here you can find that magnetic lines are forming from north pole, but they are unable to form the semi-circle. Like that way magnetic lines of force I am showing you. So here now we can say that same how magnetic field lines are formed by the bar magnet, same to same magnetic field lines forming by the solenoid. Here from north pole to south pole magnetic field lines formation is there, same as here north pole, here I drawn north pole to the south pole, here I drawn north pole, here I drawn the south poles, then north pole to the south pole magnetic field lines formation will be there, and inside of this solenoid again we can say that from south pole to the north pole magnetic field lines formation will be there. Here now arrow mark I am showing like this. Once it is coming towards here, south pole, as I am writing little upside, so you can find that such a way will be there. Then north pole to the south pole, magnetic field lines formation will be there. Again it will be passing through inside, then it is coming like that. So we can say that inside the solenoid the field formation will be from south pole to the north pole. Here as a result of it, like that way, formation of the magnetic field lines are taking place from north to south pole outside of the solenoid. Similarly here also north pole to the south pole outside the solenoid. Inside the solenoid, magnetic field lines of movement will be from south pole to the north pole. Thank you.